So the topic for today is GraphX. So when we are going to talk about GraphDB, graph computation. But before we even go to that topic, we need to step up a level above. And as I said, we want to keep it at somebody who doesn't understand anything in the graph world or big data world is fine to understand this. And there will be obviously few terms and concepts which you know before would be good, but I think we still try to keep it at that level of anybody can utilize this session. So first of all, before we could jump into GraphDB, we need to understand one level up this NoSQL world, because GraphDB is one of the NoSQL databases. So there are tons of those, and we need to understand the differences before we zoom into the graph part of it. So as we have seen in industry, databases have been there for decades and decades, several of the decades, and the favorite ones are Oracle, SQL Server, MySQL. Those are big prominent names which have been in the industry for quite some time. And life was all good till the point where the data size started exploding, and we started going into cluster kind of distributed technologies rather than having one big machine which is going to take care of that. That's what's one of the primary drivers moving towards NoSQL. There are quite a more details. I'm not keeping it a high level. So first, let's understand the differences. So the names are very familiar. We had this for, as I said, 3-4 decades. NoSQL is relatively new, 6 to 8 years, 10 years max. So that's kind of the time period. Some of them may be in different forms before there, but not in the current form. So that's the examples. The approach, as I said, is all about scalability and how we can put more data into the system. And previous approach was vertical scalability, which is like you have one machine. If you need more data to be stored, you throw that and you bring a bigger one and a bigger one. But there is a problem to that method. You cannot keep on throwing things out and in. Instead, what NoSQL and the distributed architecture does, it tries to keep you several small boxes. It's called as horizontal scaling. And we don't throw any of them. Let's say there are 20 of them and we want more storage capacity. We add 5 more, making it 25. So that's the approach. Keep on incrementally adding, and that's called as horizontal scalability. The next is about how they are dealt with. They are dealt with atomic or eventual consistency. For these, I gave a quick example. What I try to say, when you mean by atomic is your data should be transactional. That's what we mean. Let's say take an example of a bank ATM transaction which we are doing. And if you go, I go to a bank ATM and I withdraw $200 from there, what will happen? One is balance should decrease by 200, get $200 cash in my pocket. So those two transactions together. Any of them is not happening at the same time, there is a problem. There's a big problem, and that's called as atomic transactions. So that's what relational worlds do. In the NoSQL side of the world, there could be a lag depending on what it is. Few seconds, hours, or sometimes days of difference can happen, but eventually they catch up. That's what NoSQL does. Again, this is transactional systems, your order entry, your bank transactions, your products, your catalogs, all of that, versus this for analytical systems. So that's a kind of huge difference. We started with the world of relational databases with examples which I just named, and then people moved into data warehousing technologies, trying to keep the data in star schema models using Cognos, MicroStrategy, data warehousing, and all that. So this was two which were prominently done for decades and decades. All the other things are part under the umbrella of NoSQL. So NoSQL has 4 different subdivisions, if you would say, starting with something called as key value. We are not going to go in too much detail of each of them. We are zooming in focus for GraphX today, but there are other ones which we want to briefly introduce, because a lot of people have this confusion. They think NoSQL and columnar and graph is all same. It's not. The way to think about that is there is relational, which has these 2 categories, if you would think in some form. NoSQL, which has these 4 different groups within it. So key value structure, where you have a key and the whole value is stored there. It's usually your images, your video files are prominent category of things which are stored, and you could be some of the data too. The next grouping is the column family. Columnar databases like HBase, Cassandra. Instead of keeping the data in a row format in the relational oracles of the world, they keep the data in the column format, and that's where they have the name column family. Today is GraphX, and that's going to be the main focus of what GraphX is, what are the different terminologies. We'll be doing a demo in the second half of it. Some very popular names in there are Neo4j, and Stardog, and OrientDB. Vasu is going to do the demo on some of those later part of it. That's kind of the thing. Are ways to look at the GraphDB. OrientDB is the last one, which is more popular. MongoDB falls in that category. A lot of people know that. Couchbase is another example where you store each record as a separate document. Usually it's a JSON file, it's an XML file, but it's a single entity, which is a record, which is trying to store as a document itself. So that's kind of a good summary of how we really store this set of data in different formats. And depending on your use case, depending on what you're really trying to do, it's your analytical system versus whether you have dynamic schema going on, or it's more of a link connections, you will be using one of those. So we'll not go too much in detail about that because that's kind of out of scope for this topic and discussion. We just briefly wanted to introduce all the different members in this category. So next time when somebody talks to you, NoSQL and all this mumbo jumbo, you may want to bring this picture in your mind and think about NoSQL has all of these 4 different categories, and then you can bucket things under them accordingly. So I'll pause there for a second and take any questions. As I said, you can unmute yourself, ask questions, because that's a lot of information on this slide itself.
Yeah, just on the previous slide. So when you say OLTP, that's the relational one, and then when you say OLAP, that would be the distributed one?
In certain ways, yes. The relational OLTP is this, the relational database, where you have transactions. That is this, where the star schema, the data warehousing systems, where the pricing can be done by things. So that's OLAP. The OLTP is online transaction processing. OLAP is online analytical processing. For the NoSQL world.
Distributed, horizontal scaling, that applied as well to obviously the key value columnar, graph, and document, but as well as to OLAP. Is that correct?
Actually, there are lot of changes happening. Even the oracles of the world have started incorporating the SQL servers of the world have started catching up, and they are trying to do horizontal scalability because that's the only way to scale it right and like get almost unlimited kind of capacity. So these are also doing it, but originally the transactional system were not designed for horizontal scalability. They were designed more initially for vertical scalability.
So just one last follow-up question, then you continue on. So when they scaling for transactional, you still get atomic type transactions?
The behavior, yes. The behavior of the system remains same. It's just about how you can scale it. How can you add capacity? That changes based on the horizontal versus vertical.
Thank you.
Yeah, no problem. Okay, the questions. Any other questions before we move forward?
I have a question, sorry. What's the difference between OLAP and column family?
Difference. So OLAP is OLAP, which is online analytical processing. Here we are trying to keep the data. It's more tables. It's relational tables actually, but the way they are designed, which having this central fact table and all of these dimension tables. So let's say all my order data is here. The orders, how much price in each order, and then we have the products, the region, and the dimensions. In column family, it's more about how we are storing the data as columnar structure versus the relational. So it's world of difference altogether. How it is designed, how it works, completely different.
also analytical, like the column family provides the same functionality as OL.
All of them do. They do. All of these three categories, apart from the relational, provide some kind of analytical capability. Yeah, absolutely.
Okay, thanks.
Sure. Okay, let's keep moving. Now, as I said, that was taking one step up, but now let's zoom into graph world and why we should use graph, when we use graph, all that. So some of the graph examples, the most popular example actually is internet. What is internet? It's thousands of routers and computers which are connected to each other through links and connections. That's what is happening. And each of them, when you say website, it goes through several of the hosts and proxies and reaches the end server, which is hosting that website domain and giving you the results. But it has to traverse through so much path. And that is what the Graph TV does. So that's internet is an excellent example of it. Most of the time, the immediate thought comes to people's mind is social networks like Facebook or LinkedIn. Any of those categories quickly come to mind, and they absolutely use a lot of graph capabilities. Another interesting example is astrophysics, where the planets and the stars and the galaxies, the discovery of that is done through graph technology. Because if you look in a sky and you look at a particular star, it's very hard to say this star is so-and-so star just by the presence of by itself. Few of those can be done, but usually it is north of this particular 3 stars means this star. That relationship is very, very important to define what the graph locations are, the star locations are. So astrophysics uses that. So some diverse set of uses which we wanted to bring. People mostly think about social media. So that's a quick example. Let's take an example and run through it in a real life. So one of the common examples which we do is product recommendations. So product recommendations we have going in. So let's take an example of some users. So these are series of users. And on the other side, we have products or items. These users, let's say they are Amazon website users, and Amazon sells all these products. The users buy some products, and some of them, not everybody, some of them purchase stuff and also do ratings. So let's say some of these ratings are performed by the users. And in ratings, we want to give recommendations. We want to recommend the person, oh, you bought this, you would like to buy this. We recommend you to buy this as well. Ways to do that. One of the simple ways is if a camera, maybe he needs the camera card or accessories around it. So that's more very simple logic. But what if that's very standard? I think you can put a table, what are the accessories related to it, and can do those connections. But a rich kind of diverse kind of recommendations comes through this mechanism. So let's walk through that process. Let's say this person rated 2 things. He bought coffee and he has provided some ratings. What we do, one of the ways to do recommendations is go back to that system and look back, traverse back to the path, and go and see which other users have bought those products. They may have bought some other products, and we go back to that, and we traverse the third level, and it could be just keep on going on in this fashion. So they go back to that, and then they connect, and when we look into this, and we say, oh, 2 of these people have recommended a bicycle, and so our recommendation for this user would be a bicycle. I mean, nobody would have thought that because he bought a coffee and the camera, he should be recommended a bicycle, right? So that's not common sense here. That's not a rule-based engine, but it's like democratically you are letting the system put it, and surprisingly it brings a lot of much more richer sets of data than somebody trying to put in a table and say this product is related to that, because that's limited. This is a self-running engine, and actually it works much, much more powerful because people interest likings are so much. The people do similar things, I mean, and they do different things, but by doing this maximum count, more people doing this kind of behavior, so this can be done. The fourth, which was trying to put this kind of back and forth in an Oracle or a database, a relational database, absolutely humongous kind of queries. and the performance of those will not be efficient to come into Amazon sites and things like that. We think about you go to Amazon site and it's waiting to populate those recommendation engines recommendations, and it comes after 5 minutes or a few minutes. That's not a pleasant experience. It has to be performant because you want customers to buy things based on those recommendations. So your bread and butter depends on that. So that's why companies want systems practically designed for that, and Graph helps in very much in that use case. So just share some use cases, run through this quick example of recommendation engine, which is very much used in the Graph world as well. Yes?
Okay. Can you just quickly replay that animation again and how you ended up with the bicycle?
It's surprising how we ended up bicycle, but let's do it again. Okay, so this is very much the start. There's a set of users, there are items. I mean, this may not be a real case, but for this example it is. So people have bought things, they have rated things. We are trying to, specifically for this person, user by user, this is the user logged in, and we know he has bought these products. The system behind is now traversing back from those products, going to other users who bought the same product. Products or users may have bought some other products. Let's say this lady over here bought some other things, this gentleman, and so on and so forth. And we came up with this path. Now there were two possibilities: one, bicycle, and a rubber ducky. Number of lines pointing out to bicycle, that was the final choice, and that is one of the recommendations. So, I mean, this could, let's say, you are running through thousands of products, and you may say top 10. I want to show him the top 10 recommendations from this. So you have to make that choice.
Okay. Yeah, so the bicycle is going to get recommended to everybody, or just the top gentleman over on the pictures?
The top gentleman.
Okay, got it. Thank you.
He's the one logged in. It's user by user experience. It's very customized, personalized experience.
Yeah, who was actually logged in? I missed that part. Thank you.
No problem. Okay. Quick example. We talked about a few other examples, and let's dive into now how it really happens, how the magic really happens. To get that, as I said, our level base is like you have zero knowledge. We assume that you may have substantial amount of knowledge already. That's great, but that's what we are doing for level base everybody. So we need to understand some ABCs of the graph world, and that's where we start with this. So in graph, there are a few terminologies you have to understand before you get going to do anything at all. These are a few things. In the graph world, there is two main things. One is this point which is available, and this could be anything. That point could be anything. These are called as vertices. The terminology for that is vertices. Now things are connected, they can be connected, and that is called something like a line, and that is called edge. Now let's take this back in a real world environment. Let's say this is Facebook, and A, B, C, E, N, of them are people. These are people, individuals, individual people. And now let's say A is friend of B, so that is a line between that. That's the relationship. So there is a edge which is forming those lines, combining that combination. A and C are not a friend, so they are not joined in line that way. So you can visualize it that way. So and it could be anything, right? It could be a star, as we talked about astrophysics, right? It could be a star, some particular stars, how they are connected and related. You want to put that relationships. It could be website URLs. It could be hyperlinks, or it could be anything. It could be what you have. More commonly, people think of Facebook or LinkedIn kind of things, but that's easy to understand. But the concept remains same. You have points, which are called as vertices, edges, which are called as lines, lines which are called as edges. Now, a few more basic things, a few more things on top of it. When two edges meet, right? Two edges connect the two vertices, so that's kind of a line. The intersection, let's say this line CE and B, the intersection point is meaningless. I mean, there's nothing over there. I mean, it just looks like there is some intersection or something happening, but in reality, there is nothing absolutely in there. I could have put the points in a different way and they would have not intercepted. So remove from your head there is an intersection or something happening here. Possibility of a loop or a triangle, if you would say, let's say CBD, and these are all connected. They could be mutual friends, if you would think. They know each other. There is a group connected together. So that's another terminology which we need to remove. Remember, we have edges, loops. So these are three things which we want to do at this point of time. There are more things. There is path, how we traverse. We traverse from B and C if we want to reach, let's say, D or E for that matter. How can we traverse through different paths? If I want to connect B and E, I have to go from this path together. So that's kind of path traversing back and forth, which we were seeing in the previous example. But for now, let's stick with these three terminologies. You have vertices, you have edges, and sometimes it can be a loop as well. Now, several algorithms. What do we do with these kind of terminologies, or what are things which we can do? There are several of these algorithms. We are not going to go all of them, obviously, but I want to introduce to you three of them. PageRank, which is bread and butter of Google, right? And that's big butter, bread and butter, humongous amount of money coming to PageRank. There is something called as triangle count, and there is something called as connected components. So we'll talk about each of them in detail, but these are algorithms which help you do things, which help you to create scenarios and make useful applications on top of it. And first, this algorithm was created by Google, first of all, and what does it mean? Like, Google is not trying to just create you a query-based engine. It's not trying to give you search for big data and it gives you results. It does, but on top of it tries to rank that page, right? That's important. Like, what the top search, their goal is like the first one which comes out of the search has to be the biggest, the best one for you. And how do they achieve that is by looking into connections of that, the backlinks, and let's say our website, Big Data Trunk, is connected to Forbes magazine tomorrow, an article published. So our website's ranking automatically increases because we are connected to some important page. And that's how the relationship builds. So this relative self-running engine rather than somebody saying, oh, you are important and you are not, kind of a system. So that's kind of the beauty of that. Twitter and Facebooks and other things do the same thing. People who have more following, they get more priority and go up in the rank versus the other places. So
this question on the previous one. Okay, it's using the terminology of edges and vertices. So the edge is the web link connection, I guess, and then the page itself is the vertex.
Got it. Absolutely, you got it. Perfect.
Okay. Thank you.
Yeah. Thanks for bringing that and summarizing it. Great. So PageRank algorithm, I'm just going to run a small video. There is an interesting video which presents this, and I think this algorithm is talking about how PageRank is done in a very simplified way. Anybody can understand that. And they're using football game as an example inside that, and they're trying to say, and they're just literally using PageRank's logic and say which player is the best player in the field. Nobody told me you don't know this team, and you just go and say, using this data, like how these things are happening, this guy is the main person, not based on his number of goals he has done, but depending on number of passes which are happening. Each pass, player is the vertex, and the edges are the passes which are happening to each other. So that's what. And if an important player is passing to you, means you are important. Otherwise, the important player is not going to pass to you. That's the kind of underlying logic. So I'm going to run this video. Very tricky. What I'm going to do, oops. So algorithms which define and help us to create amazing applications like Google search, like PageRank, and which can be used in several places as they pointed out. Let's look at a few other ones. As I said, we'll go to 3 of them. So next one in our category is triangle count. We are defining, again, the same terminology. You have a vertex and you have edges. And once the loop is formed and at least 3 people are this connection is there, there's a triangle which is formed. Now, another interesting one which helps us to define the cohesiveness of a community. What does that mean? We talk about this community where this individual is a central person. He's very well connected to everybody, but others are not so well connected. Now, this versus, which is considered as a weaker community, says a more triangle, stronger. If you say here is only one triangle, and here there may be 6, 7, many more triangles out there. What does it do? Let's say this, I am as a marketer, I'm trying to market a product to a Facebook group, and my chances of selling this product to this group is way, way higher, because as soon as one person within this community has bought, and that does not have to be the central person, I am not relying on this one person. If it's hit or miss, I can hit anybody, and through that it just goes viral within this community. So when I'm optimizing my campaign budget, whom do I send flyer and whom I send any kind of newsletter or whatever that may be, this could be a very widely used application. I can define, okay, these are the set of out of the millions of people, these are my target audience. They are very well connected, and I can send a message, and that message will propagate throughout. It could be used in various spaces. The application to this is your imagination. That's where use case and imagination comes in. But I gave you one example and how this could be very, very powerful in marketing world. So that's our second algorithm list for today. We're trying to keep it very high level itself, but this is actually the cluster of what those algorithms are. The last one is connected components. And connected components are basically algorithms which help you to define a set of data to it, and then you just group those data, let the data sift through it and the system sift through it, and try to find what are the connected attributes or tweets. Let's say we have tweets coming into a system, and what tweet is Democratic versus Republican. So we just want to segregate that, or particular sports group, pro versus anti. All of that can be done through that, and we can start predicting now, like looking at this number of tweets happening. Oh, this is a lot of buzz around pro on this side, and that could predict the what's potentially the outcome of this or the sports event or something. And all of those interesting applications can be built on top of it. So this is another use case where connected components algorithm can be used. So we tried to sum up 3 of them. I'll just go back. We briefly talked about PageRank. We ran a video. Google does that, and many other places. Count is another one which would define how many triangles exist in our community or set of users by doing this triangle count. And finally, it's the connected components. All of these are connected in one group and this one. So this is a more profitable or stronger probability situation versus the other one. So those are 3 algorithms which we want to briefly talk. Any questions? Let me pause there as well.
And on the connected components, what's meant by lowest numbered vertex?
Question one more time, please.
Can you go back to the slide of connected components, please?
Yeah.
Yeah. On the first paragraph, the third line, it says, what does it mean when it says, graph with the ID of its lowest numbered vertex? That phrase, lowest number, what does that mean?
Right. So if we think of these tweets as a vertex, and this is 3, and this is 5. So this is the lowest one. So we got an idea of the lowest available ones in that group, whichever groups which we created. So depending on the election and things like that, this election was very exceptional, so I'm not going there. But that's what it means, the count of these.
Oh, okay, I understand. Okay, thank you.
Yeah, sure, no problem. To keeping track of where we are, we talked about generally the concepts, some terminologies, what is vertices, what is edges. That's the minimum takeaway I want you to take away from this session, understanding some of these things. These are base foundation things. And as this is our one-on-one sessions, that's our primary goal. We talked about 3 of those algorithms. There are several systems which provide that capability, whether it is Leo4j, there is StarDog, as I said. In the big data world, if you're tracking that, Spark has its own library. Spark is one of the processing engine in the Apache's framework of big data, and it has many of the libraries, and one of the libraries happens to be a graph processing, and it has all of these features, all of these algorithms built into it, and you can build on top of Spark as well. If many people in the big data world use Spark, that's why I wanted to bring that slide. So the concept part, just to summarize, that's what we did. We talked about technologies, some concepts, how those algorithms work, and then the basically the graph capability provided by Spark GraphX. So concept level at that point of time, I'll pause for more questions, but then we want to go and spend more time in the demo, which Russell is going to do, and a little bit. Any questions, any more questions or comments for so far?